So here we're going to take a look at the so-called extinction angles, or the phenomenon of extinction in minerals when we view them in a petrographic microscope. So you might remember from another video that in a petrographic microscope we have a lower nickel. And let's say that lower nickel only passes light that vibrates in an east-west direction. So we'll just draw a line that goes like this. And so as light comes in, it's vibrating in all different directions, but once it comes through, as it propagates up towards the mineral, it's only vibrating east-west. So now let's say this light hits a mineral. So we've got a chunk of mineral here. Once the light hits that mineral might have natural vibrational directions that'll cause the angle to change. So maybe instead of being east-west, it's tilted at some angle. And so now as the light leaves that mineral, it has some angle to it that's not perfectly east-west. Then we have an upper nickel, an upper polarizer filter. And let's say that polarizer is up here. Let's say that polarizer only passes light that is north-south. So we have light that's moving in this direction, and only its north-south component, so we could do a little bit of vector notation here. We have a north-south component here, north-south, not Z, and then an east-west component there. So only the north-south will be passed if we insert that so-called upper polarizer or upper nickel. I'm in the habit of calling it a nickel, so we'll call this the upper and lower nickels respectively. That's an N right there. So what happens if we take this mineral and rotate it so that even though it bends this light, we could take this mineral and rotate it like this so that when that east-west light hits it, it's also vibrating perfectly east-west. So we're going to take this mineral and just rotate it counterclockwise. So we've taken this mineral and we've just rotated it until that vibration direction is east-west. Well, that means there is no north-south direction to pass through that upper nickel. All of the light will be blocked, and this mineral will appear dark. And when it is dark, we say it is at extinction. And here's a diagram from the online textbook of Dexter Perkins, and he shows an example of extinction. So at extinction, the mineral appears dark. We rotate it away from extinction, and the light passes through. And then if we rotate it 90 degrees away from this first extinction angle, we're back at extinction again. So the mineral will be at extinction for one turn, every 90 degree turn, it will go extinct once. So there are multiple positions in which it will go extinct. Then we have the case of minerals that are elongated, and we could talk about an angle of extinction. So we can line up a mineral with the north-south crosshair. We'll just call this north-south. I keep writing Z for S, and then this is the east-west. So if we line up a mineral that has a natural elongation with a north-south crosshair, we can turn it until it goes extinct and measure that angle, and that would be the extinction angle. And then we could do the same thing with minerals that have two directions of cleavage. This guy had just one prominent direction of cleavage here, but let's say you have two directions of cleavage, one there and one there. We can measure the extinction angles, and if the mineral goes at extinction as that angle is bisected, where this angle is the same as that one, then we would say that it has symmetric extinction. Although if minerals have two directions of cleavage, that extinction doesn't necessarily have to be symmetric. So we could talk about extinction angles, and then some minerals are going to be special in showing symmetrical extinction when they have two different cleavages, and both of them go extinct when that angle is bisected. And then finally, we should mention something about isotropic minerals. Any mineral that falls into the cubic or isometric class would be isotropic. What does that mean? That means when these east-west rays hit this mineral, so you can think of east-west rays coming out and hitting some other material that's isotropic, there's going to be no bending of the light rays. If it goes in east-west, it's going to come out east-west. And so when it hits the upper polarizer, all that light will be blocked. You can rotate the mineral to any amount that you like, but whatever, it doesn't matter what angle or what orientation the mineral is. East-west coming in will be east-west coming out, and so the upper nickels will always block all of the light. So isotropic minerals always remain dark under crossed nickels. So they will always remain dark under cross nickels or XPL under cross polars, no matter how much you turn them. So you can turn the mineral, rotate them any number of degrees, it won't matter. So that's how minerals like garnet are easily identified. If you had a piece of garnet and you cross the nickels, it will remain at extinction and it will never go to full or even partial illumination, no matter how far you turn the stage. Whereas every other mineral, anything that is anisotropic, will feature this phenomena of extinction. Again, this is always under cross polars, where for anisotropic minerals, they'll go extinct, then you'll have illumination, and then extinction again, extinction at every 90 degrees. So extinction angles and the phenomena of extinction are things that we can use to help characterize and identify minerals.